Assalamualaikum warahmatullahi ta'ala wabarakatuh and a very good morning to everyone. Let's continue with our course Advanced Thermodynamics Chapter 3. This is the 5th video for this course. In Chapter 3, we will learn about pure substance. Recap of Chapter 1, we have learned 3 familiar properties of a substance, which are specific volume, gravity and heat. This is the equation for specific volume. Denotes with small case of V equal to uppercase of volume over mass equal to 1 over rho. The unit SI is meter cubic per kilogram. Basically, the objectives in chapter 3 are: we will introduce the concept of a pure substance, number of properties substance may have. We will discuss the physics of phase change processes. We will illustrate the PV, TV, and PT property diagrams and PVT surfaces of pure substances. We will demonstrate the procedures for determining thermodynamic properties of pure substances from tables of property data. We will describe the hypothetical substance ideal gas and the ideal gas equation of state. And then we will apply the ideal gas equation of state in the solution of typical problems. In addition, we will introduce the compressibility factor, which accounts for the deviation of real gases from ideal gas behavior. And finally, we will present some of the best known equations of state. Okay, let's start. What is the definition of pure substance? Pure substance is the material that has a constant composition, okay, is homogeneous and has consistent properties throughout the sample. For example, we have water, nitrogen, helium, and carbon dioxide. Pure substance doesn't have to be of a single chemical element or compounds. It can be various chemical elements. Qualifies as a pure substance as long as the mixture is homogeneous. For example, we have air, a mixture of several gases, but it is often considered to be pure substance due to its uniform chemical composition. Okay, please understand. In pure substance, it doesn't have to be a single chemical element or compounds, and the best example is air. A mixture of several gases, but often considered to be pure substance due to its uniform chemical composition. Pure substance also is a homogeneous mixtures, may be considered examples of pure substances. Examples of homogeneous mixtures included vegetable oil, honey, and air. While these substances contain multiple types of molecules, their composition is consistent throughout a sample. Okay, now you already understand the definition of pure substance. Let's see 3.2 phases of pure substance. We have 3 principal phases: solid, liquid, and gas. In solid, okay, the molecules are at relatively fixed position, where the intermolecular bonds are strongest in solids and weakest in gases. Okay, molecules move about each other in liquid phase, while molecules move about at random in gas phase. These figures shows the arrangement of atoms in different 3 phases: solid, liquid, and gases. You can see that the intermolecular bonds for gas are the weakest compared to the liquid and solid. Some substance may have several phases within a principal phase, each with different molecular structure. For example, carbon. Carbon exists as graphite or diamond in solid phase. Okay, what is phase? Okay, Phase can be identified when a substance having a distinct molecular arrangement that is homogeneous throughout and separated from the others by easily identifiable boundary surfaces. Now, 3.3 Phase change processes of pure substances. Many practical solutions where two phases of pure substance coexist in equilibrium. For example, water exists as a mixture of liquid. Water exists as vapor in the boiler, condenser of a steam plant. Refrigerant turns from liquid to vapor in the freezer of refrigerator. Okay, this is one of the example of phase change processes of pure substance. Now, let's see what are the phase change processes of pure substance. First, state 1. Okay, state 1, we have compressed liquid. Let's consider a piston cylinder device containing liquid water at 20 degrees Celsius and 1 atm pressure. Under these conditions, water exists in the liquid phase and it is called as compressed liquid or subcooled liquid. Means that it is not about to vaporize. It is just a compressed liquid. Heat is now transferred to the water until its temperature rises to 40 degrees. Okay? Heat from this candle is transferred to the water in the piston until the temperature rises to 40 degrees. So, this state is called compressed liquid. Remember, in the question or the examination, we will ask you to explain the phase change processes of pure substance. Then you have to write like this. In compressed liquid state 1, as the temperature rises, the liquid water expands slightly, and so its specific volume increases. To accommodate this expansion, the piston moves up slightly. Okay, to accommodate this expansion, where the liquid water expands when the heat is transferred. Okay, so this piston moves up slightly. During this process, the pressure in the cylinder remains 1 atm. As previously, since its pressure depends on the barometric pressure and the weight of the piston, both are which are constant. Water is still a compressed liquid since it has not started to vaporize. So, it is still in state 1, compressed liquid. Now, let's see. State 2, saturated liquid. As more heat is transferred, the temperature keeps rising until it reaches 100 degrees, state 2. At this point, water is still a liquid, but any heat addition will cause some of the liquid to vaporize. A phase change process from liquid to vapor takes place. This means when a liquid that is about to vaporize is called a saturated liquid. Okay, so in state 2, the liquid is about to vaporize. Then we consider it as saturated liquid. Now, let's see state 3, saturated liquid vapor mixture. Midway of the vaporization process, the cylinder contains equal amounts of liquid and vapor. This phase referred to as saturated liquid vapor mixture, since the liquid and vapor phases coexist in equilibrium states. See this figure, we can see the saturated liquid and saturated vapor is equal amount. Now, in state 4, okay, in state 4, after state 3, saturated liquid vapor mixture, state 4, saturated vapor. Once boiling starts, the temperature stops rising until liquid is completely vaporized. Means that the temperature remains constant during the entire phase change process if the pressure is held constant. As we continue transferring heat, the vaporization process continues until the last drop of liquid is vaporized. At this point, the entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat loss from this vapor will cause some of the vapor to condense. A vapor that is about to condense is called saturated vapor. Okay, state 4 is saturated vapor, where the vapor that is about to condense. Now, let's see state 5, superheated vapor. Once phase change between liquid to gas, which is vapor, complete, we are now back to a single phase region again. However, this time is vapor, not liquid. Further transfer of heat results in an increase in both temperature and specific volume. At state 5, the temperature is 300 degrees, for example, and if we transfer some heat from the vapor, the temperature may drop. However, no condensation will take place as long as the temperature remains above 100 degrees. A vapor that is not about to condense is called superheated vapor. Okay, in state 5 means superheated vapor. Now, let's see the T-V diagram for phase change processes of pure substance. Just now, we already learned the phase change processes from state 1 until state 5. Okay, let's see the TV diagram, temperature and specific volume for the heating process of water at constant pressure. So what is V? Unit of V. We already learned that in chapter 1, and I also already recapped at the earlier video. Okay, so in TV diagram, first we have first state, compressed liquid. Liquid is not about to vaporize. The diagram should be like this. Okay, then after compressed liquid, we have state 2, saturated liquid. Okay, it's here, saturated liquid. Water exists as a liquid that is ready to vaporize. And then we have state 3, saturated liquid vapor mixture. Okay, so the liquid and vapor phases coexist in equilibrium states. So it should be like this. It should be here, between 2 and 4. State 4, we have saturated vapor, where the last drop of liquid is vaporized at 100 degrees. A vapor that is about to condense. And then we have state 5, superheated vapor. A vapor that is not about to condense. Alright, now let's see what is the definition of saturation temperature and saturation pressure. See this statement. Water boils at 100 degrees. Do you agree with this statement? Actually, the perfect or correct statement is water boils at 100 degrees at 1 atm pressure. 1 atm pressure equal to 101.325 kilopascal. Why I say like this? Let's see this figure of a piston system. If the pressure inside the cylinder were raised to 500 kilopascal, by adding some weight on top of the piston. Okay, water would boil at 151.8 degree. Thus, the temperature at which water starts boiling actually depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. At a given pressure, the temperature at which a pure substance changes phase is called saturation temperature, or the symbol is Tsat. At a given temperature, the pressure at which a pure substance changes phase is called the saturation pressure. Okay, so saturation temperature and saturation pressure. This is the liquid vapor saturation curve of a pure substance, and we can see from this table saturation or boiling pressure of water at various temperature. So if the temperature is 100 degree, then the saturation pressure will be 101.4 kilopascal. Okay, now let's see the definition of latent heat. Latent heat is the amount of energy absorbed or released during a phase change process. Remember, okay, during the phase change process, latent heat is responsible, okay, for the phase change process. More specifically, we have latent heat of fusion and latent heat of vaporization. In latent heat of fusion, the amount of energy absorbed during melting means that from solid to liquid, it is equivalent to the energy released during freezing. How about latent heat of vaporization? It is the amount of energy absorbed during vaporization from liquid to gas, and it is equivalent to the energy released during condensation. Now, let's see property diagrams for phase change processes. We have one system, a piston contains of water at 1 atm pressure and 20 degree. As you can see from this figure, as heat is transferred to the system state 1, this system follows a process path as we learned previously. Let's add some weight on top of the piston, and we will find the pressure increases. Let's say up to 1 megapascal. Okay, from 1 atm to 1 megapascal. As heat is transferred to the system, the process follows a path that is very much similar to the process path at 1 atm. However, there are some noticeable differences which can be observed by the TV diagram. Okay, let's see. Now we have the same diagram. Okay, each line represent different pressure at different points. Okay, then here for this line, it's actually same with this one that we learned previously. This one, okay, is the same. However, this one is for P equal to 1 atm. Okay, but then here we have different pressure value. Okay, from pressure equal to 0.01 megapascal up to pressure equal to 25 megapascal. Alright, so now TV diagram of phase change processes of a pure substance at constant pressure. Numerical values are for water. Okay, we have a saturated liquid vapor. Okay, here at this line, this straight horizontal line is saturated liquid vapor mixture, saturated liquid line, and also superheated vapor region. Okay, in these two regions, the substance that exists in single phase, either liquid or vapor, saturated vapor line. Okay, here it's different with this one, saturated liquid line and saturated vapor line. Alright. At 1 megapascal, okay, at 1 megapascal here, the water starts boiling at higher temperature. Okay, At higher temperature, the water start boiling. Okay, and then the specific volume of the saturated liquid is larger, and the specific volume of the saturated vapor is smaller than the corresponding values at 1 atm. Okay, and then as pressure is increased further from 0.01 megapascal up to 25 megapascal, the saturation line this saturation line continues to shrink. You can see it is shrink. Okay, it's larger down at the down part, but then it's smaller at the top part. Okay, so it continue to shrink until pressure reaches 22.06 megapascal. Okay, in case of water, so this is the critical point. Okay, critical point for water is pressure equal to 22.06 megapascal. Okay, what is critical point? Critical point is the point at which the saturated liquid and saturated vapor states are identical. So they don't have any saturated line here like this, but then the saturated liquid and saturated vapor are identical. So it is called critical point. Okay, it denotes with TCR, PCR, and VCR. And then as pressure above critical point, okay, as pressure above critical point, we have pressure equal 25 megapascal. Specific volume of the substance continually increases. Okay, so here we can see the specific volume continue increase. Okay, we have specific volume here, so it continue increase, and only one phase present, usually refers as superheated vapor at temperature above critical point. So the name is superheated vapor at temperature above critical point. It is not superheated vapor region only, but then superheated vapor at temperature above critical point. Alright, so here we can see the zoom at this position, at this region. Okay, we have a critical point and critical pressure above critical point. Here we have a vapor, superheated vapor. Alright, all the states that involve both phases in equilibrium are located under the dome, called the saturated liquid vapor mixture region or the wet region. So this is the dome. Okay, all states that involve both phases in equilibrium are located under the dome, called the saturated liquid vapor mixture region or the wet region. Okay. Alright. So this is the PV diagram of pure substance that you learned before, and this is the PV diagram of pure substance. It is actually identical, but this one is pressure and this one is temperature. Okay, so this represents pressure and this one represents temperature. Okay, you can see the difference. Okay, the difference between the line, the diagram, and also you can see the dome here. Okay, so for PV diagram, the lines like this. Okay, then superheated vapor to downside, and then TV diagram, the lines like this. Okay, the superheated vapor region is to the top and increase. Okay, most substances contract during a solidification, i.e. freezing process. Other substances such as water expand as they freeze. Okay, so this is the PV diagram of a substance that contracts on freezing and PV diagram of a substance that expands on freezing. For example, water. Okay, it's a little bit different. You can see the diagram, okay, here and also here, this region. Okay. Alright, extending the diagrams to include the solid phase. Water expands upon freezing. Okay, so actually this statement gives a vital consequences. If water contracted, okay, if water contract, not expand, on freezing as most substances do, the ice form would be much heavier than the liquid water, and it would settle to the bottom rivers, lakes, and oceans instead of floating at the top. So it will be very dangerous. So that is why The water is actually expands upon freezing. Okay. Another example, how does aquatic life survive in extremely cold condition? Okay. When the temperature of atmosphere falls below 0 degree, the water at the surface gradually freezes to ice, but the water under ice layer remains at 4 degree. Fishes and aquatic life survives due to anomalous nature of water. Okay, the one that we discussed just now. Ice being lighter than water floats and insulates the water below it from freezing. So because of the water expand during freezing, then the ice float. Okay, the water ice floats and insulate the water below from freezing. Now let's see for 3.4, extending the diagrams to include the solid phase. Okay, under some conditions, all three phases of pure substance coexist in equilibrium. Okay, three phases means vapor, liquid and solid. Okay, on PV or TV diagrams, these triple phase states form a line called the triple line, or in PT diagrams, it appears as a point. Hence, is often called as triple point. The states on the triple line of a substance have same pressure and same temperature, but different specific volumes. Okay, remember on PV or TV diagram, it is it is a in form of line, okay, called triple line. However, for PT diagram, it appears as points, so we call it as triple point. Okay, let's see the triple point temperature, triple point pressure for water. Okay, for triple point temperature, 273.16 Kelvin, and triple point pressure is 0.61 kilopascal. Okay, so this is PT diagram. PT diagram. So it appears as a point. So here is the point, triple point, where the solid, liquid, and vapor coexist each other, coexist in equilibrium. Often called as phase diagram, since all three phases are separated from each other by three lines. Alright, so in PT diagram, the sublimation line separates the liquid and vapor region. Okay, the vaporization line separates the liquid and vapor region. Here. Okay, this is sublimation. The melting or fusion line separates the solid and liquid region. Solid and liquid region. This is the melting or fusion line. Alright. These three lines meet at triple point where all phases exist in equilibrium, as I explained before. Okay, sublimation. What is the definition of sublimation? It is passing from the solid phase directly into vapor. Okay, from solid direct to vapor phase. At low pressures, below the triple point value, solid evaporate without melting first. Okay, so that is the definition of sublimation. Without going to the liquid phase, it directly went to vapor phase from solid. The vaporization line ends at the critical point because no distinction can be made between liquid and vapor phases above the critical point. Substances that expand and contract during freezing differ only in the melting line here on the PT diagram.